you may or may not have covered balancing redox equation in Chem 200. You should have when you covered types of reaction. But if you didn't, then we're going to cover it here because it's an integral part of electrochemistry. So let me go ahead and start this. And the first part is simply understanding some of the vocabulary in electrochemistry. Some of the things that you should know is, and let me just forewarn you that it's not difficult in terms of electrochemistry, but it can be confusing. And the reason why it's confusing is because when you're dealing with electrons, you're dealing with negative particles, negative charge. And so whenever you're donating an electron, then you would think of donation. Something that receives it would be a positive thing, but it's a negative particle, so it's going to be negative. Things always seem opposite in electrochemistry. So you got to get that clear in your mind that a reducing agent, a chemical that is reduced, is actually the chemical that is going to be positive because it loses electron, and that it's going to be responsible for reducing a chemical. When you reduce or oxidize, think of reduction and oxidation in terms of the charge. When you have a reduction, then you increase your negative charge. If you increase your negative charge, that means you're gaining electron, okay? Oxidation is you're increasing your positive charge. If you're increasing your positive charge, that means you're losing electrons, okay? So you can see why it seems opposite, because electrons are negatively charged. So when you oxidize, you lose electrons, so you have more protons than electrons, and therefore that species is going to have a greater positive charge. So just think about that, because yes, electrochemistry, until you are really immersed in the vocabulary and the practice some of the problems, will seem confusing, okay? Because electrons are negatively charged. You do have an experiment in the lab where you do some electrochemical reactions and you figure out how to establish a standard reduction potential table. Anyway, let me go ahead and get here. That way we can cover as much material as we can here. So we're looking at electrochemistry, and remember that we are dealing with transfer of electrons. We're looking at a species or a chemical reaction that releases an electron, and we're looking at a chemical reaction that gains electrons. So here's a typical example. A stands for an anion, and when it gains the electron, when it loses an electron, it becomes positively charged. An example of that might be sodium. Sodium will lose an electron. By losing an electron, it becomes positively charged. An example of a species that is reduced might be a halogen, fluorine in this particular case. When it gains an electron, it becomes negatively charged. So I have a cartoon there showing how sodium becomes sodium ion, fluorine becomes fluoride ion, and then the positive and negative are going to be attracted so that you have an ionic species. That's how ions form, okay? One particle is charged, the other particle is charged, and then they don't form a bond, they form an electrostatic attraction for each other. So remember from the fundamentals of 200 and 152 that when you have sodium chloride, or in this case sodium fluoride, it's not a sodium fluoride bond, it's a sodium surrounded by as many fluoride as possible, and then it's a fluoride surrounded by as many sodium as possible, depending on the stoichiometric ratio. In this case, it's 1:1. Okay, so we have that for our, it's not really NAF. There's no such thing as an NAF species. It's an NAF crystal lattice structure, and that's a formula unit, So oxidation is the process in which a species increase its charge. Reduction is the process in which a species gets reduced in its charge. Okay, so in this particular case, here's another example. Iron goes to iron plus 3, loses electron, it gets oxidized because the charge is increasing. Yet in the process of becoming +3, it loses electrons. It has to deliver its electrons. So the oxidation reaction is the reaction responsible for delivering the electrons. Therefore, it's responsible for reducing the other partner. That's why it's called a reducing agent. The oxidation reaction is the reaction responsible for delivering the electron. Therefore, it's called the reducing agent. On the other hand, if you look at oxygen here, you'll see that by gaining electrons, it's going to get reduced, okay? And yet it needs to gain those electrons by pulling the electrons from its partner. So the fact that it's receiving the electrons means that it's an oxidizing agent. Without that reaction accepting the electron, the partner will not be able to get oxidized. So the reduction reaction is also the reaction in which you have the oxidizing agent. The oxidation reaction is also the reaction in which you have the reducing agent. See how it's confusing? You just have to think about the process. Take a step back, think about what's going on. One species is giving up electron, the other species is accepting electron. Okay, so that's what I mean by it seems backwards. Anyway, when that happens, then you have these ions that forms, and then they come together and form an ionic species. In this particular case, you have iron oxide, which is nothing more than rust. Okay, it's nothing more than rust. But it's pretty interesting for those of you who went to the seminar on Tuesday. They're now using iron as a form of material for batteries. So that would be promising because we got so many iron. Iron is a bountiful element. It's not like cobalt where it's sort of scarce and the prices go up and down. Iron, sometimes it's just within. Iron easily rusts and reacts with oxygen to form iron oxide. So oxidation process, the charge increase, reduction process, the charge decrease. It's also called the reducing agent. The reduction process is also called the oxidizing agent, okay? It's a symbiotic relationship. If you're going to have an oxidation process, you're going to have a reduction process because a species will not be able to get rid of its electron if there's no partner to accept it. A species will not be able to accept electrons if there's no partner to deliver it. So it's got to be symbiotic relationship. You cannot have one without the other. Now, theoretically, okay, and sometimes we do this when we're doing problems, we can just say, okay, let's take a look at this reduction reaction. That's a reaction which gains electrons, remember? And we're not even looking at the oxidation reaction. We're just assuming that it's going to gain its electrons some way or the other. And so we can write what we call a half reaction for that. And you guys will see what I mean by that. And you can actually calculate an electrochemical potential for that half reaction. But in the real world, it has to be coupled. You have to have an oxidation and reduction reaction. Theoretically, on paper, you can just deal with one or the other and then figure out what the other is. But in the real world, you're going to have both reaction symbiotically relating to each other. So you can't have one without the other, in other words, okay? So that's what I'm talking about right here. Now, the other thing that you guys should know how to do is be able to assign oxidation state. What are oxidation state? It's the charge of a species, the most common charge for a species, or a charge that a species would have if it releases its electron or if it gains its electron, okay? And there's certain rules about oxidation state, and let me remind you about those rules, okay? Go back here. The oxidation state of a species that you find in nature in its natural form is 0. Like you find iron. in nature. The oxidation state of iron, pure iron, is 0, the element, okay? Sodium, elemental sodium is 0, but sodium in sodium chloride is +1. Iron in iron oxide is +3, but just the natural species as found in nature has an oxidation state of 0. Hydrogen, found in nature, H2, the oxidation state is 0. Okay, so that's what we mean by the first rule. Free states. The oxidation charge of group 1 generally is +1. That's the most common. Group 2 is +2. Group 7 is -1. Okay, and then the others can vary. They have variable oxidation state. Fluorine is your most electronegative element. Fluorine is your most electronegative element. So therefore, fluorine will always have an oxidation state of -1. In other words, it's going to have a species that really is attracted to electrons. Remember, a -1 means that fluorine is attracted to electron. The fact that it's the most electronegative element means that it is going to pull electron from whatever it's interacting with. Oxygen is your next most electronegative element, and it prefers 2 electrons. But there's such a thing as peroxide and superoxide. Peroxide has oxygen with an oxidation state of -1, and superoxide oxygen has a oxidation state of -1/2. Okay, -1/2. Hydrogen prefers to be +1. And then remember this rule: the sum of the charges of a neutral species, a neutral ionic species, is going to be equal to 0. So you can figure out the oxidation state for each of the element in a species, like potassium permanganate, KMnO4. What is the oxidation state of all the elements there? Well, we know that oxygen is our most electronegative element, so that's -2. The fact that it's -4, I mean, there's 4 of them, means that that oxygen is going to be -8. The 4 oxygens -8. The potassium, figure out the oxidation state of elements that you know. Oxygen and group 1, potassium +1. So therefore, the transition metal is going to be figured out by default. We know that oxygen in this chemical is -8. We know that potassium is +1. Therefore, manganese has got to be +7. Why? Because this whole thing is going to be a charge of 0 because it's an ionic species. Ionic species, as found in nature, is going to be a neutral species. So the sum of the charges, it's basically what we call electrical neutrality. Manganese +7, hydrogen, potassium +1 equals the 4 oxygen at -2 apiece. Okay, so that's how you figure out oxidation state. And here's a periodic table that shows common oxidation state. Okay, let me clear this. And then there's a movie here that shows you what the oxidation state for certain elements are. Like group 1 is always going to be +1, group 2 is going to be +2. The middle are going to vary depending on what it's partnered with. The other thing you should remember is that zinc is always +2, cadmium is always +2, silver is always +1, aluminum is +3. Okay, so you could review that. Anyway, the movie's there. I'm not going to show you the whole movie, but it's available on the PowerPoint slide. Okay, here are certain summary of the oxidation state. Now, we use that information so that you guys can balance oxidation reduction reaction. Do not try and balance oxidation reduction reaction by inspection. That's what you guys learn in Chem 200 by looking at a reaction and going back and forth so that the elements on both sides are equal. That's how you balance a chemical reaction. In an oxidation reduction reaction, you have to account for electron transfer. And the electrons that is transferred has to be the same between the oxidizing species and the reducing species. If one reaction is going to deliver 3 electrons, the other reaction must accept 3 electrons or a multiple of that by balancing the equation. Okay, and so let me give you an example. What I am teaching you is something called the ion electron method. Some of you may have seen balancing redox equation by the charge method. That's sort of guesswork in my thinking. The ion electron method is a little bit maybe more involved, but you always get the right answer if you follow the recipe. And I'm going to show you the recipe. And it's pretty easy. Okay, it's pretty easy in terms of that. So we're doing this under acidic conditions, which means that H plus is available. And you might say, well, why if it's under basic conditions? We'll take care of that. Okay, what if it's under neutral conditions? Remember that we are always working with aqueous medium. All the reactions we have talked about in this course is under aqueous medium, which means water is involved. Okay, it's not until you get to organic chemistry in which we look at organic medium. Here we're looking at aqueous medium, and when we have water, we have both H plus and OH minus available through the auto-ionization of water. Okay, so we're looking at acidic conditions first, and then if it's under basic conditions, we will correct for that. So the first step that you should do is you should take a look at that reaction and then identify the oxidation reaction and the reduction reaction. You got to split it into two half reactions. Now you might say, well, how do I figure out which is the oxidizing and which is reducing? Don't worry about it, okay? But what you do need to do is take that redox reaction. Redox just stands for reduction oxidation. Okay, so we call reduction oxidation or oxidizing reduction reaction redox. You take your redox reaction and figure out a way to get both half reaction. When you figure out the half reaction, then one of them will be an oxidation and the other one will be a reduction. Which is which? You figure that out when you balance the electrons. Okay, so first thing you want to do is take a look at that reaction and then write the half reaction. That's the number. Don't even balance it. Well, before you even do that, make sure that the chemical formulas are correct. If you got the wrong formula, then no, not worth balancing. You're going to be wrong. Okay. If you put, for example, you have perchloric acid and you write HClO3, then it's going to be wrong. You got to write HClO4 for perchloric acid. Okay. So make sure you get the formula correct before you start. That's always the fundamental thing to do. And then break it up to your half reaction. Then what you want to do is you're going to have to balance the half reaction separately. Concentrate at one half reaction at a time. When you start balancing the half reaction, balance the non-hydrogen and oxygen elements first. That is, balance all other elements except for hydrogen and oxygen. You save that for the next step. Okay, so if there's 4 tin on one side, make sure you have 4 tin on the other side. Okay, balance the non-hydrogen and oxygen elements first. Then you want to balance the oxygen element next. Okay, and you balance the oxygen by water. Why water? Because you can't just throw in oxygen. Okay, can't throw in oxygen because maybe oxygen's not available, or because it's in water medium, but oxygen's available through water. So you balance oxygen through water. Okay, and then you might say, well, then that means I've introduced H plus or hydrogen. Well, that's okay, because your next step is to balance the hydrogen by H plus. That's why it's under acidic medium. Okay, and then when the non-hydrogen and oxygen elements are balanced, when all the oxygens are balanced, and when the hydrogens are balanced, then you balance the charge. And you can only balance charge by electrons. So if you got a positive, you can't add protons. You have to put electrons there to reduce that positive. If one side is +3 and you got to get it down to 0, then +3, if you put electrons on the other side of the equation, +3 and -3 are not equal. Okay, positive 3 and negative 3 are opposite. What you need to do is, if one side of the reaction is 0 and the one side of the other side of the reaction is positive 3, you put the electrons with the positive 3. That way you get it down to 0. So both sides are 0 now. Okay, so when you balance the charge, you got to make sure that both sides of the reaction have equal charge, not equal and opposite, equal. Positive 3, negative 2, negative 2. It doesn't matter what the charge is, as long as it's the same. It could be positive 30 and positive 30 for both sides. Doesn't matter, as long as they are equal, not equal and opposite. Okay, not equal and opposite, equal. So that's very important. And then what you want to do is you do that for the second reaction. And then when you combine it, you got to look at the number of electrons. If one reaction has 3 and another reaction has 2, then you got to multiply those half equations so that the number of electrons are the same for both half reactions. So you multiply the reaction with 3 by 2, and you multiply the reaction with 2 electrons by 3. That way you have 6. Then when you combine them, the electrons will cancel. Okay, the electrons will cancel. And you can't have a net electrons in your overall equation. They have to cancel. The other thing you will notice when you do this method is that the electrons are going to be an opposite side. It's going to be natural. The electrons are going to be an opposite side. So if the electrons are in the reactant side, okay, then that's the reduction reaction, because an electron on the reactant side means that the species is going to accept that electron and gets reduced. If the electrons are on the product side, that's the oxidation reaction, because that species is going to be giving up electrons and releasing it to the other half reaction. So when electrons are in the product, then what you are doing is you are losing electrons. If you lose electrons, oxidation. Think of the mnemonic device Leo. Leo the lion, okay, is what I always tell my students. Leo the lion, or Leo the astronomical sign for your horoscope. Lose electrons, oxidation. But what does Leo do? He gurs. Okay, all lions, well, they don't really gur, they roar, but just say they gur. And gur is gain electrons reduction. GER, gain electrons reduction, lose electrons oxidation. So that's how you know how to identify the oxidation or the reduction reaction. Okay, so when the electrons is in the reactant side, that's going to be your reduction reaction. When the electrons is in the product side, that's going to be your oxidation reaction. The oxidation reaction, just to confuse you more, is your reducing agent. The reduction reaction, just to confuse you more, is your oxidizing agent. Okay, so again, let me show you an example here. Okay, at the 2-half reaction, the electrons should cancel. So what we're going to do is we're going to start with this reaction right here. Iodine is going to get, see how you have I minus, and the oxidation state on I2 is 0. So the charge goes from negative to 0. That's the oxidation. Okay, because the charge is increasing. That's your oxidation reaction. If you look at S2O8, it goes to S2O4, and they're both -2. So you might say to yourself, well, then how is that the reduction? What you need to do is you need to figure out the oxidation state of the element. So what we have here, if just for the sake of to show you how I would work this out, let me change my pen here. There's 8 oxygen at -2 apiece. That's -16. That means each sulfur, okay, you always work with the most electronegative element first, or the element in which you know the oxidation state. Group 1, group 2. Aluminum, cadmium, silver, zinc. Okay, that means that each sulfur is +8. Here, what we have is oxygen. There's 4 of them, so that's -8. Okay, oops, let me clear that. I forgot one thing. Okay, I forgot one thing. Sorry about that. The whole thing, minus 16 plus what equals minus 2. Okay, it has to equal minus 2. So what plus minus 16 is minus 2? Well, that means that this is 14. That means each sulfur is positive 7. Okay, the sum of the charges of the chemicals in the formula has to equal the total charge. Okay, now if that was neutral, then sulfur would be positive 8, but it's not neutral, it's negative 2. So we do the same thing on the other side. You can see that oxygen's minus 8. What plus minus 8 equals negative 2? That's going to be positive, in this particular case, 6. Okay, positive 6 plus minus 8 is negative 2. That means each sulfur in this particular case is positive 3. Okay, so you can see that sulfur is the species that gets reduced. It goes from positive 7 to positive 3. Iodine goes from negative 1 to 0. That's the oxidation. Sulfur gets reduced. So that's how you would play this game of figuring out the oxidation state if you had to. But I'm sort of going off on a tangent again, but I wanted to demonstrate that. I'm going to clear this. Okay. So this is your half reaction. This is your redox reaction. The formulas are correct. Iodide is I minus, iodine is I2, S2OH, thio sulfate, S2O4 is persulfate. Okay. And what we're going to do is balance the half reaction. One half of the reaction is going to be I minus to I2. The other half reaction is S2O8 minus 2 going to S2O4 minus 2. We'll attack one half reaction at a time. For the iodine, what you see here is that all you've got to do is balance the iodine. So you put 2 on the left side. Okay, there is no hydrogen or oxygen, so you can skip that step. And then now we balance the charge. The left side has negative 2. So you need to put 2 electrons on the right side. Okay, now the element and the charge are balanced for that. 2I minus goes to I2 plus 2 electrons. Then we work on the second half reaction. The second half reaction looks like this. I'll clear this for you. What you would have is S2. Let me go back here, okay, so that you can see the work that is involved, because I want to walk you guys through this. So the second half reaction would be S2O8 minus 2 going to S2O4 minus 2. Remember to balance the non-hydrogen and oxygen elements first. The sulfur is already balanced. Go to the next step. So non-hydrogen and oxygen first. Then balance oxygen by water. So here we have 8, here we have 4. So we need to have 4 H2O on this side. That gives 4 oxygens. Okay, so now the sulfurs are balanced, the oxygens are balanced, and then balance the hydrogen by H plus. So if we look at this, we see that we have 8 H plus on the right side. We need to put 8 H plus on the left side. Okay, so now we have all the elements balanced. 2 sulfurs on both sides, 8 oxygens on both sides, 8 hydrogens on both sides. We balance the charge next by electrons. And remember, you can only add electrons. You cannot take away electrons. You can only add electrons. So what we need to do is we need to look at this side. This side's plus 8 minus 2. That side's plus 6. This side is negative 2. So what you will do typically, and I've seen students do this, okay, they would put 4 electrons here, and then they will tell me that minus 6 and positive 6 is balanced. No, remember what I told you, okay? They have to be equal, not equal and opposite. They have to be equal. So if you put 4 electrons on the right side, that's not correct. That's especially true because if you recall, the electrons on your previous reaction is also on your right side. It can't be on the same side. Can't be in the same side. It's got to be on the opposite side. So let me just clear this so that you can see the proper way of doing this. Okay. So again, we go back and say that this right here is positive 6. This is negative 2. What you need to do is you need to bring the positive 6 down to a negative 2. The only way to do that is add 8 electrons here. By adding 8 electrons on the left side, the 8 electrons and the positive 6 now makes this whole thing negative 2. And a negative 2 and a negative 2 is balance. Is balance. Okay. And what you will see, let me clean this up for you so that you guys can see this. I'm going to erase this and erase that. What you will see is that between the two reactions, this has 8 electrons, this has 2 electrons. They can't cancel. You got to multiply the top reaction by 4. You got to multiply this reaction by 4 so that now this becomes 8. This becomes 4, of course, and this becomes 8 as well. Only by doing that will the electrons cancel. And then you add the 2-half reaction. So the electrons have to cancel. The electrons have to cancel. So let me clear this up so that you can see the PowerPoint, how the PowerPoint plays out here. So here we have 8 electrons. Here we multiply the top reaction by 4, so we have that. And then when we add the 2-half reactions, you can see that the electrons will cancel. We see that we can just put it together. We have basically this as our balance equation. The last thing you should do is double check everything. Check the iodine, 8 iodines in both sides. Okay, 8 I minus equals 4 I2s. Check your sulfur, 2 sulfurs on both sides. Check your oxygen, 8 oxygens here, 4 plus 4, 8 oxygens there. Check your hydrogens, 8 hydrogens here, 8 hydrogens here. Check your charge. This side is -8, -2, that's -8, +8, that's 0, and -2. This side is -2 as well. You work so hard to get to that point. If you just leave it alone without double checking, and you made a simple arithmetic mistake in the previous step, it's going to be counted wrong, especially in multiple choice question. So as the last thing you should do is double check your work and make sure all the equations are balanced. Okay, so pretty straightforward, I hope. Okay, but it is tedious. You have to follow the cookbook recipe. If you do that, you'll be able to balance your redox equation. So let me move on and tell you under basic conditions. Under basic conditions, instead of H plus, what you will have is OH minus. Okay, so the steps are identical as if you were balancing it under acidic conditions, except for the very last step. Okay, so this step right here is pretty much identical to what I already talked to you guys about, except for the fact that we now need to introduce this reaction right here. You need to eliminate H plus. Why? Because it's not under acidic conditions. And the way you eliminate H plus is by adding reaction. H plus plus OH goes to water. That's the autoionization of water. So if you have a reaction, let's say you have a reaction here. So this is your reactant and this is your product. And let's say that you have 4 H plus on the left side. Let me change my pen. You got 4 H plus on the reactant side. Then the way you use this equation right here is you need to put the 4 H plus on the product side. Only by putting it in the product will it cancel. So if the H plus in your, when you add your 2 half reactions on the reactant, the H plus has got to be in the product. If the H plus is on the product side, then when you add this reaction right here, the auto ionization of water, the H plus has got to be in the reactant side. They can only cancel that way. Anyway, this is what you would do. For every 4 H plus, you also include 4 OH minus, and you also include 4 waters. Okay, it's a 1-to-1-to-1 ratio. The H plus will now cancel, and what you want to do is just add this reaction right here to the previous equation. And now H plus is substituted to OH minus. Now you're under basic conditions. That's the only step that's the only added step you need to do under basic conditions. Okay, if the problem doesn't tell you what the conditions are, just assume acidic conditions. Okay, but if it specifically tells you under basic conditions, then you need to add this reaction right here, this reaction right there. Okay, so let's take a look at that type of problem. Okay, here we have the hydrogen peroxide and dichromate. Dichromate Cr2O7, and it produces chromium and oxygen. Okay, so the reaction would probably be chromium going to Cr2O7 going to chromium, and the other half reaction would be hydrogen peroxide going to oxygen. Those are the 2-half reaction I would write. Anyway, you can go through this exercise. I'm not going to go through it because I need to rush through this so that I can get to electrolytic cells. But let me at least talk you guys through this. So this is your first reaction in which we balance the dichromate to chromium. Of course, dichromate's got oxygen. So you need to throw in water in there to balance the oxygen. When you throw in water, you bring in hydrogen. So you got to bring in H plus in there to balance the hydrogen in water. And then, of course, we balance the charge with electrons. Notice the electrons are in the reactant side. So when you gain electrons, that's your reduction reaction. That's your reduction reaction. And you could probably figure that out by figuring out the oxidation state of chromium in that species right there. I won't do that, but what I want to show you is the very last step. What do you do under basic conditions? The next step is hydrogen peroxide. Hydrogen peroxide goes to oxygen. Oxygens are balanced. Okay, don't throw in any waters. Then you balance the hydrogen with H plus. So we throw in 2 H plus in there, and then we balance the charge. And then in order to get the charge correct, you notice we have 2 electrons here and we got 6 electrons there. So we need to multiply the bottom reaction by 3. And when we do that, this is what we have. And then we just add it. Okay, so that's your net reaction. But this is under basic conditions. You notice that the hydrogens are right here. So the way you convert this to basic conditions is you need to add 8 hydrogens here and 8 hydroxides here, and it's going to have 8 waters. So when you add this reaction, the hydrogens will cancel, but the waters will also cancel because you got 7 here and you got 8 here. So this becomes 1. And then just add the half reaction. You have 3 hydrogen peroxide plus a dichromate plus a water goes to 2 chromiums plus 3 oxygens plus 8 hydroxide. Double check your work as a very last resort. Now what you have here is the reaction under acidic conditions converted to the reaction under basic conditions. It's that easy. If you want to convert a reaction from acidic to basic, you're just adding H plus OH goes to H2O. That's all you're doing. And you need to add it in a way so that the hydrogens are going to cancel. Okay, the hydrogens are going to cancel. So this is what the results that you see in my PowerPoint slide. And that's the net reaction right there. Okay, so here are more examples. Now, I'm going to spend a couple of minutes on this right here because what I found out is that you guys are pretty good in following recipes or directions. The hardest part in doing redox equation is figuring out what the half reactions are. Okay, you guys in lab have an activity where you have a whole bunch of equations and you practice balancing them using the method that I showed you. Okay, so what I want to show you here, or at least talk to you guys about here, is how to get started with the half reaction. Okay, because it's always not obvious, like I showed you in the previous example. Okay, it's always not a one-to-one correspondence. Let's take a look at this reaction right here. What are the half reactions for that? What are the half reactions for that? Well, you would say that, okay, let's start with potassium permanganate, KMnO4. KMnO4, it's got potassium and permanganate. Okay, so we got to look for the species with potassium permanganate on the product side. So here is potassium right there, and that's the only place where we have potassium. So we got to bring in KCl. Okay, why? Because that's the only species on the product side that has potassium. No other place has potassium. So now we can balance the potassium. But notice, in the process of bringing in potassium, we also brought in the chloride. You cannot bring in potassium by just writing K plus. You cannot just say, oh, this is just K plus. Okay, because that's not the species that's shown in the product side. Yeah, that's the species, that's the element, but not the species. So you can't do that. You can't do that. You have to bring it in as KCl, because that's what we have in the product side. The problem with that is you also bring chloride. And so you have to also bring chloride on the reactant side. Now you can balance potassium and chlorine because you have both elements on both sides. Okay, but we still have one more problem. We have permanganate or manganese, Mn. Okay, so we have to bring manganese as well on the product side in order to make sure that we have non-hydrogen oxygen elements on both sides. We have the potassium, we've got the manganese, and we got the chloride. Now we can balance this half reaction right here. It looks more complicated than a half reaction, but that's what you need to do. Okay, that equation now can be balanced using the steps that I showed you. What's the second half equation? Well, we've used this guy and we used this guy right here, and we use this guy and we use this guy. This is the only species we haven't used. So that means our second reaction is Cl2. Where does Cl2 come from? The only species on the reactant side that has Cl is HCl. So that's your second reaction. Yes, we can use HCl for both half reaction. It's not limited to just one. Okay, you can, some HCl might react to help the oxidation reaction. Some HCl will react to help the reduction reaction. It's okay to do that. So that would be our half reaction. Okay, that's why getting started is sometimes the most difficult. Let's take a look at this reaction right here. In that case, we have the iodine going to IO3 minus, and we got the iodine going to I minus. So the species I2 can be involved in both half reactions. Why? Because you don't have just one I2. You've got moles and moles of I2. Some I2s will get oxidized, some I2s will get reduced. Okay, so it's okay to do that, but you need your half reactions. Let's take a look at this. Chromium will do that. Okay, CrO4 will go to Cr hydroxide. How about oxygen? That's a peroxide right there. Well, you say that, okay, chromate will be that. Actually, this is more involved because what element in what chemical in a redox equation is always available? Water. So this reaction probably was completed by water. Water will do that. It's not obvious in a redox equation, but know that you always have water in these redox equations because you're doing it under aqueous medium. This is a problem that you guys will see in your activity. This reaction is pretty typical. That one's easy. The iron is going to go to iron plus 3. The MnO4 will go to Mn. Okay, so that problem is easy. So this in here, I kind of talked to you guys about how to start or how to determine your half reactions. Okay, make sure that when you pick one species, that all the elements on that species is going to show up on the product, especially the non-hydrogen and oxygen. Don't worry about the hydrogen and oxygen. They'll balance by water and H plus. But if you've got tin, iron, and sodium, the other side's got to have tin, iron, and sodium as well. Otherwise, you'll never get that thing to balance. Just like in this example right there. Okay, just like in that example right there. So practice that. Here's a whole bunch that you guys will see in your lab. For those of you not in lab, you should still practice this. Just go to the lecture notes and practice that. You get, like I said, once you understand the recipe is easy. It's getting started that's difficult. What are my half reactions? So let me switch gears here and get to electrolytic cell. At least get started on that. Okay. The rest of this you guys can take a look at. So let me go ahead and move on to the next section here. And again, the lecture notes for this is over here, redox, reaction, electricity, and then we're going to be covering voltaic cell. Voltaic cells, it's just a fancy term for batteries. It's basically reactions that in which electrons is able to be generated. And you know that when you push electrons in an external circuit or move electrons through a wire, you can do work, and then you can get some machines to work. Okay, so voltaic cells are nothing more than battery. They're also known as Daniel cells. So let's take a look at that. So this is where we are right here. Okay. So when you're talking about voltaic cells, here's a typical example. You guys, some of you may or may not have seen that TV episode Breaking Bad. Okay, there's one scene where they're cooking meth. Okay, so it's basically a chemistry high school teacher who cooks meth because he needs the money. Okay, that's not your typical chemist. There's some garage chemists that might try and do that, but that's not how we're generally not on the dark side. Although we have the ability to be in the dark side by figuring out, because the chemical reaction is not that difficult. Okay, it's getting the ingredients, but that's all I'm going to say about that. But anyway, Breaking Bad's about this high school chemistry teacher that hooks up with this guy, and now they're cooking meth and making a lot of money. So they need to go to a place where the chemical fallout, the residue, can't be detected. So they go out to the desert, buys a mobile home, goes out in the desert, and they start cooking this meth. And because he's a chemist, it's one of the most purest meth that is in the market. Okay, at least that's what's happening. Anyway, they're out there cooking meth and everything, and then their battery dies on their Winnebago, and they're like probably hundreds of miles away from civilization. They gotta get somehow they gotta get their Winnebago going. So he uses his chemistry knowledge again to make a battery. And what does he do? He uses copper and zinc. Use copper and zinc in this particular case, and this is basically it in terms of that. Or maybe he uses iron and zinc. Anyway, you can use different materials, and if you plan it just right, you can get an electron to flow through an external circuit as one species gets oxidized, the other species gets reduced, and then you can do work for you. Okay, so if your ambitions is to be a chemist, then you too will have knowledge about making batteries, or you don't have to be a chemist about to do that. You can actually make a battery from potatoes or lemons. And you guys probably have seen that in these uh, science project in grade school. Anyway, let's take a look at this reaction. This is your typical reaction in terms of generating electricity. We have zinc and copper. Why? Because one species here is really good in getting rid of its electrons. Another species is really good in accepting electrons. So we have a species that is really good in being oxidized. We have another species here that's really good in being reduced. So if you take a zinc and put it into a solution, and that solution has copper ions in it, then what will happen over time is that the blue color here is actually an indicator of copper ions. Copper ions, and you guys may have seen this in maybe previous examples. Copper ions is blue in water. Okay, but when you reduce that concentration, then the blue lightens up, and then you get the copper solid plating out, and the copper solid looks brown or looks like it's rust, but it's really a copper solution. So that reaction will happen because what's going on is that the copper is getting reduced, going from copper +2 to copper 0, and the zinc is getting oxidized. It's going from zinc 0 to zinc +2. So what you will see here is that the metal is going to corrode and the copper is going to build up. So that's basically what's going on at the molecular level. Okay. Now, if we just put two solutions together, okay, where we have zinc and zinc sulfate here, maybe we have zinc sulfate here, and we get copper and copper sulfate here, then we can get that reaction to go, but then it'll stop. And the reason why it stops is because the electrons are going to get transferred here, and then you get a charge buildup. Whenever you have a charge buildup, that's going to be like a barrier to stop the electron from flowing. You gotta complete the circuit. It's the same reason why you need to switch the switch on your home to turn on a light, because when it's off, the circuit is open and the electrons aren't free to move around. As soon as you close it, then the electrons can move about, turn on your light bulb, and then go back out into the ground. Okay, but that's basically how electricity operates in your home. You turn it off, you open up the circuit, the electrons can't flow anymore. You close it, you close the circuit, the electrons can flow and it can do work. So here you have an open circuit, the electrons can't flow, your reaction is not going to go. What you need to do is you need to complete the circuit. And the way you complete the circuit is you basically would put what we call a salt bridge for the two, so that any electron buildup on this side is going to be counteracted by any ions. Positive ions is going to neutralize it, and then the negative ions will go over here, so that any positive deficit on this side or positive buildup on that side is going to be neutralized by negative ions. So we need a salt bridge to complete the circuit, in other words. Okay. Oops, I apologize for that. Yeah, thanks. Okay. Yeah, sometimes I get carried away in talking to you guys. So like I said, this is the reaction in which the zinc is going to get oxidized. And here what you have is that blue color turns lighter because the ions is going to diminish, and now they form copper solid. So that's what's going on here. Okay, and then here we have this circuit, and if we just connect the two, here we have zinc sulfate, copper sulfate, connect the two, then it's not going to work because the electrons will build up on one side, and then the electricity is going to stop. We have a barrier for the electron to transfer. So we close that barrier by putting a salt bridge, and the salt bridge will complete the circuit. And now the electrons at least charge will be available to flow. And that's what we have in a battery. Okay, in a battery, we have something called an anode and a cathode. And what eventually will happen is that electrons will be generated from the anode. That's where electrons originate from. And then they'll go to the cathode. Okay, but in the process of doing that, it's going to go through an external wire, and then it can generate, it can do work for us, like start our engine. So that's what we have right here. Okay, that's what we have right here. This is a typical battery. We have our zinc, and we have our copper. The place that undergoes oxidation, remember, zinc is going from 0 to +2. That's the oxidation reaction. So the place that undergoes oxidation is always your anode. Oxidation. Now this is for a voltaic cell. This is for a voltaic cell, is the anode. That's where the electrons originate. Okay, that's where the electron originate. And the anode's negative. Anode, think of anions. Anode, anions. Anions are negative, right? So that's where the electrons originate. And then they can go through this electric external circuit right here. Can go through this external circuit right here. Okay. It can do some work, or you can read it through a voltmeter, and then it heads to the copper, and the copper accepts it, and the copper gets oxidized. It goes from copper +2 to copper 0. So what's going to happen here is that the copper is going to start plating out over here. Then there's ions here. This is your salt bridge right here. And because there's a buildup of negative charge on this side, it's got to be counterbalanced by the sodium migrating to that side. Okay, the electrons build up. It's got to be counteracted by positive cations flowing to that side. That means that the negative anions are going to be flowing on to the left side to counteract the fact that this side, because it's losing electrons, is going to start building up its positive charge reservoir. If it's increasing its positive charge, then the negative ion is going to neutralize that. So that's the flow of the salt bridge. It's got to have ions in it, and those ions got to be made from strong electrolytes. They need to be able to break apart. And then one side is going to get a migration of positive ions. The other side is going to get a migration of negative ions, so that everything is complete and there is no charge buildup. Okay. Again, the side that undergoes oxidation is called the anode. The side that undergoes reduction is called the cathode. This is where reduction occurs. Remember, reduction, gain electron reduction, GER, lose electrons oxidation, LEO. So when you gain electrons, this is where electrons are being gained, right there. You got your reduction. That's your cathode. Remember, cations are positive charge. Okay. The cathode's also labeled red. The anodes are black. If you look at your battery, okay, if you had problems with your battery like I had a couple of weeks ago, okay, one is your car battery, that is. One is negative, one is positive. If you're going to jump your battery because your battery is dead, you hook up your cathode for your cathode first, your positive, and then you hook up your anode last, and then you don't really touch it to the negative terminal. You connect it to the metal of your car. That way, if there's spark, there's no spark in the vicinity of the battery, because the battery sometimes will generate hydrogen gas. And if it generates hydrogen gas and there's a spark there, it could explode. I've never seen a battery explode, but that's what they tell you. You connect to one car, you put your positive and negative. To the car that needs to be jumped, you put your positive terminal first, that's your cathode, and then you take your negative terminal and you connect it to one of the metals on your car, and then you can start your car. Okay. Then they tell you, This is on the side, but they tell you that the first car that's supplying the battery shouldn't be running. Why? Because they say that now with all the computer parts to your car, it might send a back charge to that other car and then ruin the computer. It's never happened to me. I've always run both cars, but just so you know, there's a lot of practicality to batteries. Anyway, this is a battery right here. This is what um, your AAA battery, your AA battery, or car battery will have. It's basically transferring electrons from one to the other through a chemical reaction. Okay. So this is a summary of what I just talked to you guys about. Anodes, black, negative electrodes, generates electrons, oxidation occurs. This is your cathode red, positive terminal, accepts electrons, reduction occurs. Here it is again. In this particular case, we have this particular setup. This salt bridge now is here, and it's just basically what we have is just a semi-permeable membrane so that the ions can migrate to both sides. Sign convention. We have the oxidation reaction, okay, the anode, and we have the negative terminal, the cathode, and you'll be able to generate a certain amount of voltage from that reaction. In this particular case, under standard state conditions, notice the super zero right here. Under standard state conditions, you generate 1.10 volts. And where does that come from? It comes from the 2-half reaction. The 2-half reaction is zinc going to zinc plus 2, and it's going to have a certain E0 1/2, okay, or just an E0 for that particular reaction. And what we also have is copper plus 2 going to copper 0, and that also has an E0. And we can put 1/2 in here because it's half the reaction. Sometimes we just put an E0 for that particular reaction, okay? And whatever these values are under standard state conditions, it's going to add up to 1.10 volts. So that's how you determine how much voltage you would get from a chemical reaction. You look up the electrochemical potential for that reaction, and it's all tabulated in the appendix, or the appendix in your lab manual or your lab book. Okay, so in this particular case, this is what it is. For the zinc undergoing oxidation, it's 0.76 volts. For the copper undergoing reduction, it's 0.34 volts. And when you add those two, you theoretically get 1.10 volts. Okay, now 1.10 volts is not enough to start your car. You need 12 volts to start your car. So what you do is, for those of you who've taken physics, you need basically 12 cells in parallel. Okay, you connect one of these reactions to another, and then the cumulative sum of these reaction will give you 12 volts. So that's how you would do that. Anyway, that's it right there. I'm going to stop there and continue on, because these are really important topics. That is how to calculate electrochemical potential from your half reactions, from your oxidation reduction reaction. So I'm going to stop there and then continue on here and talk to you guys how to read the standard. Let's go to standard reduction potential table. Okay, it's standard reduction potential table. How to read that so you can calculate these values right here for a redox reaction, because sometimes it's not obvious how to do that, especially based on the convention I give you and the convention the textbook gives you. They're both the same, but you approach it differently. Okay, so I'm going to stop there because it's about 6:15, and then finish this off next time. Like I said, we can't have your next quiz this weekend. We just don't have enough time to cover both voltaic cells, um, and free energy and voltaic cells. What I do want you guys to do is we'll probably not cover electrolytic cells. So you are on your own in reviewing that. If we have time next week, I'll briefly cover it. Okay. And then talk to you guys a little bit about batteries. But that's all I really wanted to talk to you guys about. I apologize for covering my iPad with the screen previously, but I'll talk about that again. Okay. So for those of you who submitted that work last week on that work that I asked you guys to do, the solutions are up. Just go to that assignment and you'll see the work shown there. Okay. Again, no quiz this weekend. It's delayed a week. Okay. Thank you very much. Yeah, that one, if you click on the link in the announcement, it should have gotten you to where you would upload it. Okay, for you to do that. Always go to the announcement page because I generally provide a link for you to submit that. But I'll give you guys another one. Thank you guys, and we'll see you next time. Okay, bye for now.